Right now, somewhere in the world, an engineer is staring at a bug they can't explain. Their sensor is working, their code looks fine, but the program keeps missing things. A button press, a timing window, a signal that was there for just a fraction of a second. And what's the worst part? It doesn't fail every time, just sometimes, randomly, maddeningly. That kind of bug has a name. It's called a race condition. And it almost always comes down to the same root cause. The code is trying to watch everything by itself, one line at a time. The fix is to stop making your code watch and let the hardware do it instead. That's exactly what timers and interrupts are for. Let's start with timers. A timer is a hardware counter built into your microcontroller that increments at a fixed clock rate, completely independent of whatever your code is doing. It just counts up and up at a precise frequency all by itself. On an Arduino Uno, which runs at 16 MHz, the timers count in sync with that clock. The Uno has 3 timers: timer 0, timer 1, and timer 2. Timer 0 and timer 2 are 8-bit, meaning they count from 0 to 255 and then overflow back to 0. Timer 1 is 16-bit. It counts all the way to 65,535 before overflowing. You've already been using timers without knowing it. The millis and delay functions in your Arduino, those run on timer 0 in the background. That's why delay blocks everything. It's literally just sitting there waiting for the timer to count up. Nothing else in your code runs. Now, counting at 16 MHz is incredibly fast. Most of the time you don't need that precision, and the numbers would overflow constantly. That's where prescalers come in. A prescaler divides the clock before it reaches the timer. Set a prescaler of 64 and a 16 MHz clock becomes 250 kHz to the timer. Set it to 1024 and you're down to about 15.6 kHz. Slower counts, longer time before overflow, which is exactly what you need for PWM frequency control or measuring longer time intervals. Okay, now interrupts. This is where things get really powerful. Here's the problem with normal code. Your loop runs top to bottom, over and over. If something happens between 2 lines, a button press, a sensor trigger, a timing event, your code might completely miss it. An interrupt solves this by telling the microcontroller, stop whatever you are doing right now and run this specific function instead. When that function finishes, the microcontroller goes straight back to exactly where it left off, like nothing happened. This function that runs when an interrupt fires is called an ISR, an interrupt service routine. You write it just like a normal function, but you attach it to a specific trigger. Here's a real example. Say you want to detect a button press instantly, no polling, no missing clicks. Attach interrupt takes 3 arguments: the interrupt pin, the name of your ISR, and the trigger mode. Rising means it fires when the pin goes from low to high, which is exactly when a button is pressed. Now, no matter what your loop is doing, even inside a delay, the moment that button is pressed, button ISR runs immediately. But interrupts aren't just for external signals like buttons. You can attach them to timers too, and this is where it gets really useful for embedded systems. A timer interrupt fires automatically every time the timer overflows or hits the specific value you set. This lets you run a piece of code at a perfectly consistent time interval, without delay, without blocking, without missing a beat. For example, fire a timer interrupt every 1 millisecond and inside the ISR update a sensor reading, check a state machine, or toggle an output pin. Your main loops keeps running freely, handling display updates, serial communication, whatever you need, while the timer interrupt handles the time-critical stuff in the background. This is how you get a microcontroller to appear as if it's doing multiple things at once. It's not truly parallel, but it's fast enough that nothing notices the difference. So where does this actually show up in the real world? PWM generation. As we covered last time, Arduino's analog write uses a timer underneath. The timer toggles the pin automatically. Your code never touches it. Servo control. Servos need a pulse every 20 milliseconds, precise to a microsecond. The timer interrupt nails the timing perfectly every single time. Rotatory encoders. These spin fast and generate pulses rapidly. A polling loop will miss pulses at a high speed. An interrupt catches every single one. Real-time data logging. A timer interrupt fires at a fixed interval and samples your sensor. Your data is perfectly evenly spaced in time, which matters a lot when you are doing any kind of signal processing or filtering. Now, one critical rule about ISRs: keep them short. While an ISR is running, other interrupts are blocked. If your ISR takes too long, you'll start missing events, corrupting timing, or producing bugs that are incredibly hard to reproduce and track down. The right pattern is set a flag inside the ISR, then handle the actual work in your main loop where the timing pressure is off. Also, any variable shared between your ISR and main code must be declared volatile. Without it, the compiler might optimize the variable away entirely and your code will behave in ways that make absolutely no sense. Timers and interrupts are what separate reactive, reliable, embedded code from a fragile, polling loops that just hope for the best. Once you start thinking in interrupts, you look at every project differently, because now you know how to guarantee timing, not just approximate it. Try it yourself. Wire a button to pin 2 on an Arduino Uno, attach an interrupt, and notice how it responds instantly, even when your loop is stuck in a delay. That moment of it just working, that's a good one. If this clicked for you, hit subscribe. Next time, we are going into I2C and SPI, the two protocols that let microcontrollers talk to sensors, displays, and other chips. See you then.